So welcome to our advanced seminar on managing uncertainty in evolving geospatial data. This is a joint tutorial by Andreas Züfle from George Mason University, Gotche Trajcevski from Iowa State, Dieter Pfoser from George Mason, and Joon-Seok also from GMU. So what's this tutorial about? Let's begin with a slide that none of you have ever seen. One of the 4 V's when it comes to big data is veracity. Now, data quality is a big issue when trying to utilize data as an asset, which is something our economy is increasingly based on. Now, the scope of this tutorial is not to examine uncertainty in relation to data in general, but to focus on spatial data and even more so on novel spatial data sources. So as such, following an introduction, our tutorial has 3 main parts. Part 2, as it's marked here, is on uncertainty in spatial data as we know it. Part 3 discusses new data sources and how to deal with them. Part 4 finally talks about geosimulation, because sometimes our knowledge of the real world is limited and we have to resort to simulation to complement our knowledge gaps. The question becomes, of course, how good or accurate those models and simulations are. To put it bluntly, spatial data can be fake news. Mike Goodchild, more than 20 years ago, points out that we typically ignore the uncertainty associated with our data when he states that spatial uncertainty is the Achilles heel of GIS that, when exposed, can bring down the entire house of cards. And he doesn't mention lawyers in this context. Keep in mind that Mike back then was talking about data sets that are curated by experts. So the question is now, who is actually creating the data and why spatial data is actually important. So spatial data is important not only when it comes to classical data sets such as road networks and land use data, but also as a means to structure information. So keep in mind that a lot of content has a spatial aspect, and this can be exploited in different ways and also by different services. Spatial data traditionally has been produced by authoritative sources such as USGS or the Ordnance Survey in the UK and local and state governments. The data was then shared with restrictions, copyrights, and came many times with a hefty price tag. So what has changed in the last decade when it comes to data generation? Data producers are now everywhere. Instead of having few companies and agencies generating the data, a great number of web services and mobile applications turns virtually everybody into a data producer. Sometimes even without their knowledge, but that's another story. So how is this new kind of data generated? Volunteer geographic information is a term that was coined by Mike Goodchild back in 2007 and refers to crowdsourcing spatial data through dedicated efforts. The biggest example here is OpenStreetMap, also known as the Wikipedia for spatial data. So it began all in 2008 in the UK and has grown since beyond a simple vector data set of the global road network, as it also includes specialized efforts such as cycle maps and, important for many, point of interest data. As with any crowdsourcing service, OSM has data quality issues, like in this example, phantom cities. There are several ways to address data quality issues in OSM. One is to rely on the wisdom of the crowd to help reduce uncertainty and the errors in the data. Other efforts are the use of super users and more formal methods to detect problems and fix them also in the data. Another crowdsourcing example is user traces. Tracking users can help improve a range of services such as navigation. The resulting data can be trajectory data generated by tracking vehicles on a road network. Although one can see the road network in this example, from an algorithmic point of view, the path that a vehicle took with respect to the road network is less than obvious. From an uncertainty perspective, things get worse if we look at user trajectories as recorded by check-in data, such as in this case tweets. Where was the user for this data in between position samples? And the samples can be hours apart. Trajectory data also has 2 basic errors. The sampling error speaks to where an object was in between position samples. This generates an error ellipse with possible positions in between samples. And then there's the measurement error. For example, when using GPS, this error can be a few meters. When the position is further obfuscated, it can be several kilometers. If we know of any constraints, such as that the movement occurred on a network, then we can employ, for example, map matching algorithms to reduce the error and uncertainty in the data. Of course, there are many other sources of error and uncertainty when it comes to movement. For example, we might lose the GPS signal in urban canyons or indoors. Specific positioning technology might only be available at certain locations, wireless sensors with large positioning errors indoors, and there is always human error when it comes to crowdsourcing. Talking about research challenges, we want to consider uncertainty with the data and as part of our queries. We want to assess the quality of the results that we retrieve from, for example, data mining methods. And overall, we want to improve the service quality and the quality also of our research when it comes to using the data.
Thank you, Dieter, for your introduction and motivation. This is Andreas, and I will give you a brief introduction to managing uncertainty in spatial data. This seminar was originally planned for 90 minutes, so I will focus on a selection of main concepts and ideas. In an uncertain database, the attributes of an object are random variables. And just like there are discrete and continuous random variables, there are discrete and continuous models for uncertain data. In discrete models, each object is described by a finite set of possible instances, or alternatives, each associated with a probability mass. For example, object B here has two possible alternatives, each having equal probability of 0.5. In continuous models, an object is described by a continuous function that maps each location to a probability density that describes the probability per areal unit of the object being in this location. In summary, both models describe the uncertainty of the location of an object. In some cases, you may not be sure if an object exists at all. In this case, the total probability mass may sum up to less than 1. You may have noticed already that the possible instances of object A sum up to only 0.8. That implies that there is a possible world having probability of 0.2 that object A does not exist at all. This case is called existential uncertainty. To query uncertain data, one might say, why not simply use the mean or expected location of objects? Why even bother to consider possible alternatives? To answer that, consider this example. Uncertain object U has two possible alternatives, U1 and U2. There are three more objects A, B, and C, which have no uncertainty. Now consider the following query. What is the nearest neighbor of U? In this case, there are two possible database instances, or possible worlds. In one world, U is located at instance U1. In this case, A is the nearest neighbor of U. In the other world, U is located at instance U2. In this case, B is the nearest neighbor of U2. Each possible world has a probability of 0.5 here, so our answer is object A with a probability of 0.5 and object B with a probability of 0.5. Note that there is no possible world in which C is the nearest neighbor of U. But if we were to use the expected location of U, which is shown here, we would return C as the nearest neighbor of U. However, we already know that this is, in fact, not only an unlikely, but an entirely impossible result. You may imagine that, in a spatial database, such cases may lead to inconsistencies, such as the expected location of a vehicle being inside a building or a lake. Now, let's go from uncertain spatial objects to uncertain spatial databases. An uncertain spatial database is a collection of uncertain spatial objects. In the example on the right, we have three uncertain objects. Object A has three alternatives, including the alternative of not existing. Object B has 3 alternatives, and object C has 2 alternatives. As each uncertain object is a random variable, an uncertain database is a random variable as well. The sample space of this random variable is defined by the set of all combinations of object instances. These combinations are called possible worlds. On the right, you see that there are a total of 3 times 3 times 2 equals 18 possible worlds, each differing in the locations or existence of objects A, B, and C. Let us look at a larger uncertain spatial database. Here we have 26 uncertain objects. Let us assume that each object has 5 possible alternatives. One way to answer any type of query on uncertain spatial data is to enumerate all possible worlds. What you can see here now is how each possible world is processed. We look at the 25 combinations of objects A and B, and then we combine these with the 5 instances of object C, then the instances of object D, and on the bottom left down here, you can see the current counter of the number of possible worlds processed so far. And this way we can answer any query. No problem. That's not good. Well, clearly there are too many possible worlds to process. Due to the combinatorial number of possible worlds, such naive query processing is infeasible, even for very small toy datasets. And indeed, Dalvi and Sushio have shown that general query processing is sharply hard in the size of the database. So is all hope lost? No. While general query processing is hard, it is still possible to find polynomial time solutions for specific query types. And fortunately, many spatial query types, such as range queries and nearest neighbor queries, have polynomial time solutions. There are many elegant tricks that allow to find analytical solutions for these query types. However, this advanced seminar will not discuss these in detail, and the interested audience may find details in recent tutorials and surveys. In the next part of this advanced seminar, I will instead look into approximate solutions using Monte-Carlo simulation. In the last video, we saw that running a query on each possible world is infeasible. In this video, I will discuss a simple solution, simply using a random sample of possible worlds to infer results on the full population of all possible worlds. Remember that I said in the last video that processing k-nearest neighbor queries on uncertain data can be done in polynomial time. Well, that statement is both true and false and depends on uncertain query semantics. To understand uncertain query semantics, consider the following small example dataset. In this example, we have 2 uncertain objects, Q and B, having 2 alternative locations each. We further have 4 certain objects. Consider the following question. What are the 2 nearest neighbors of Q? I will give you a few seconds to think about it. There are 2 different ways to interpret such a query, and I wonder which one you chose. Let's look at the object-based variant first, which asks, for each object, what is the probability to be part of this result? If you interpreted this query this way, your result may look like this. For example, object D and E have a 40% chance to be part of the 2 and n set, depending only on the location of Q. If Q is located on the left, then C is guaranteed to be in the result. Note that C is closer to Q1 than A, and B or A may also be results depending on the location of B. An alternative interpretation of this query is result-based. What is the probability of each possible result set? If this is how you interpreted the query, then your result may look like this. The result is guaranteed to be D and E if Q is on the right, and otherwise, the result is AC or BC depending on the location of B. Now, the object-based interpretation can be answered in polynomial time. However, the result-based interpretation cannot. For a simple proof, assume a K&N query in a database where n objects are uniformly distributed across the data space. In this case, any of n choose k results have a non-negative probability to be part of the result and need to be reported. In the next slides, I will give you an intuition how to approximate result-based query semantics using Monte-Carlo simulation. The first two steps of this approach are as follows. First, we randomly sample a set of n possible worlds and compute the query result in each of these sampled worlds. Each sampled world is a certain database, and as long as our query has a polynomial time solution on certain data, this approach has a polynomial time solution as n is a constant. Now, there is a problem. There is an exponential number of possible worlds, right? And those may all be different. Thus, it is almost surely to happen that all sampled worlds may have different results. So how do we aggregate them? You can't count them because they might all be different. The idea is to cluster all these possible results. For this purpose, we map the results into a result space. For K&N query, that would be the space of all K sets. For this clustering, we need a similarity function between results. For K&N queries, this similarity function could be Jacquard set similarity. Once we have clustered these results, we can report what is called representative results. That is, results that are similar up to a specified threshold to a large number of sampled possible worlds. Inferential statistics can then be used to provide bounds for the probability that the unknown true result is similar to a representative result. For example, for a 5 nearest neighbor query, a representative result may state that with a probability of at least 85%, the true result differs from result set A, B, D, E, F by a Jacquard set distance of at most 1. More details on the idea of answering queries on uncertain spatial data using representative query answers can be found in a recent SSTD paper. And that concludes my part, but we are not done yet. So far, I've only talked about spatial data without any notion of time. In the next videos, Gotze will discuss managing spatiotemporal or evolving spatial data. Thank you.
Thank you, Andy, for passing the baton. Hello, everybody. I'm Gotze, and welcome to the third part of our advanced seminar today. The focus of this part will be on the fact that in addition to the location data and spatial distributions, we will worry about the location in time and sometimes the accompanying context. So we'll focus on moving objects, which is things that change their spatial whereabouts in time, and they can be anything of interest, not necessarily point data. But we'll start with a point location data. Now, the first question is, what is the source of uncertainty? And most often it's the very location detection and the technology relying upon. GPS, for example, has a well-known inaccuracy in terms of reporting locations, whether it's an urban or wildlife environment. In addition, we have the issues related to how regular is the sampling, how the regularity of the sampling is affected with changes in the motion, and can we always assume the coverage. In urban environment, we can also have location sources based on inductive loop sensors or roadside sensors. The point, though, is that their precision is quite sensitive to the density of the traffic. But then again, what the heck, they're at least in the road network, and in such scenarios we can also rely on the floating car data, The question is, though, can we make use of both of them? Can we combine them? And then sometimes we can say, well, what about the good old cellular data? That is well known to be imprecise when determining the user's location. So, first thing first, we know what location and precision is all about. How do we model it together with the motion? And then, the moment we pick the model, how does that affect the syntax, semantics, and the algorithms for processing the queries? One of the models is the so-called sheared cylinder model. What it does is it assumes that the object, whenever its location is reported, is actually somewhere within a disk centered at the reported location. In between, assume the linear motion, and then you have the concepts of possible routes or whereabout, or possible motion curve in time. Another model that was studied by the geographers too, and then spatial-temporal community, is the so-called bead. Essentially, if I know your location at a given time and I know the limit on your speed, the best I can hope for is that you're somewhere within this cone as time goes by. However, the moment I get the location update from you at a given time, then applying the reasoning backwards, I know that in between those 2 points you could have been anywhere in the intersection of those 2 cones. And when projected in 2D, that gives the ellipse that Dieter mentioned in the first part of this advanced seminar. Now, if you have some extra knowledge, like road network constraints, then we can adopt the model and then have this origami-like structure in between 2 updates of the object's location. Now, we pick the model. How does that affect the queries? Well, it affects them in a sense of what is it that the user can hope for to get in the answer. So for example, if we have the bead model and we're interested in spatial-temporal range query, the best we can hope for is to tell the user that, you know what, you could have been there possibly sometimes, or you know what, you could have been there at all the times, not only at some point of time, depending on your motion, because all I know about you is that you're within an ellipse. If we have the sheared cylinder models, then we have to somehow convey to the user that there is probability of anybody of the red, green, or dark object being a nearest neighbor, and here is how those probabilities are ranked, and here is how the ranking of the probabilities changes over time. If there is a road network, then again, the best we can say is that at a given time point, the object was somewhere along a certain segment, or, given a location, there was a certain begin time and end time that the object could have been there. And we work our way from there to answer the question. Now, the flip side of uncertainty is, what is it that you need? What is it that your application demands? So we have inductive loop sensors, and that's all nice and dandy, but are you interested in macroscopic models, or microscopic, or somewhere between the mesoscopic? Are you interested in modeling the pedestrians too? Or are you happy with some grid and having a knowledge about inflow and outflow with respect to cells and their correlation? Because the clustering that you can do, the prediction that you can do, is just good enough if you're Uber. Or do you want some finer level of clustering, in which case, maybe instead of road segments, you should consider lane distribution, and then realize that, although there is increased density of traffic, it only affects one lane, while the others have a good speed. Then the next question is, are 2 uncertainties always better than 1? Sometimes yes. Basically, if everything that I know about you in between updates is that you're within some ellipse, but I also get the data from inductive loop sensors, in which case I know that you're somewhere along this line segment B prime, B double prime at a given time, then putting the 2 together, instead of having a single cone, a single bead rather, I will have a sequence of shapes that are more precise than cones and that look like teardrops. Then what about enriching the motion with some textual descriptions? Well, if that is the case, I have additional worry. When you tweet near temple, which one is it? Can I put together the previous location update of yours and narrow down? Or when you say that the object is like a museum, then I have to worry about semantic similarity and semantic relatedness and figure out a way to narrow down your possible whereabouts or the possible descriptors of the object. Now, when it comes to non-point objects, a very common scenario is being interested about the evolution of a shape and what is the boundary of the uncertainty and the boundary of the uncertainty of the boundary of the shape. So what we see here, for example, is we're interested in how a disease was spreading to a crop. Or we may be interested to predict how the fire will spread so that we can plan to allocate the firefighting resources. Typically, there is always a source, some measurements. And what we're interested is which measurements in which locations, over time of course, are exceeding certain threshold value or are satisfying certain property. Now, the imprecision of measurements is always going to be there, but in addition, now we have to worry that the measurements are taken only in discrete locations. We have to worry that we will always have only approximated shapes or boundaries, and if the data is enriched, we can still have errors in the descriptors of that shape. So, for example, here, we know that we would have certain phenomenon indicating red zones, like high temperature, but we also know that the best we can do is approximate it with a polygon. We know that we can have certain spatial imprecision of the data, but we also know that descriptors such as population, salary, roadworks and all, they vary over time and they're also imprecise. If we ignore the time for just a second as a dimension, we have this Tobler's law by the geographers stating that everything is related to everything else, but near things are more related than distant. And when we want to do some kind of a surface analysis, we really would like to have this smooth, nice little wave, vector-like, quadratic polynomials to avoid the discrepancies or the sharp turns that triangulated irregular networks introduce. But alas, again, the measurements are only taken in discrete locations. So a common approach to model this is to use a distance-weighted average, or the method known as kriging. What we see here, for example, is using measurements in only 7 points to infer the value in the other 18 of those 25 locations that are approximated by cells. Clearly, we need to incorporate the values measured at a given location, as well as the distance of that location from wherever we want to interpolate or estimate. And for that, there are plenty of probabilistic models describing not only the error due to the imprecision of the measurement itself and the distance, but also some white noise of an error. Another issue that spatial entities that evolve are concerned with is the heterogeneity of the sources, like we see in this example. We know the preferences of a herd in terms of the rainfalls and the altitude. And then if we know some observations that are currently valid, we can predict how the habitat is going to move in the next time instant. The problem, though, is that these data sources have quite different rate of evolution, and each and every one of them may be having different uncertainty descriptors that we know of. Now, when it comes to the spatial granularity, that's one issue. The other problems stem from the fact that we have contextual heterogeneities, like we see here, a bunch of different sources just to estimate the underground water flow from irrigation through precipitation and so on. So the issue again is, what is the model that we want to use versus its applicability for a given domain? Are two krigings always better than one? How hard it is to fuse them? Can we model the evolution of the kriging itself? What we see here is what brought us to virtual Paris, COVID. We have two completely different data sources trying to describe the evolution of the same phenomena. One of them is trying to model the recovery based on a context, so it involves graphs and spatial structure. The other one involves some genomic epidemiology. So we could try kriging, co-kriging, multi-scale integration. But then we're facing the risk of the so-called ecological fallacy, which is, by aggregating, we could make quite a wrong prediction about an individual. Now, the last flip side of the uncertainty is sometimes we want to compress the data. We want to use 3 instead of 8 points to represent this motion. Or we have to compress because of the energy of a transmission. Well, we introduce uncertainty. Sometimes the basic assumptions of the model fail. What if the driver violates the speed constraints that we use to calculate its speed? And sometimes we completely cannot explain the uncertainty. To close this part of our advanced seminar, I'm going to introduce one example that will lead you to the next portion that Joon is going to tell you about, a different kind of uncertainty. And the scenario is a stellar evolution, or a binary stellar. You know, sometimes the stars start spinning around each other, start exchanging matter, gases, mass. Sometimes they end up one being a black hole sucking the other. The point is, the temporal domain available for actual observation is very, very tiny in relationship to the evolutionary temporal domain of billions of years. So, we must resort to simulation, and those are huge data sets that are very rich, hundreds of parameters of interest, and the uncertainty is very natural in the sense of how shall I select initial parameters? What is the granularity of the grid? What is the impact of a time step? Should I do a compression? What is the error on the nearest neighboring cluster? But again, Joon is going to take you quite further in the world of simulations.
In the previous module, we saw how to model uncertainty in spatial data and spatial temporal data. Spatial objects in uncertain database are random variables. Since there are too many possible worlds, we sample them from a statistical distribution. How can we deal with the more complex phenomena with uncertainty, such as human behaviors and social interactions? To this end, various approaches have been developed to simulate complex phenomena. In this module, I'm going to demonstrate how can we use geospatial simulation as a tool to handle uncertainty. Especially, I will focus on the agent-based modeling approach. Based on observation, we build a model that imitates a real-world complex system to understand the system and solve various problems. We simulate a model to explain how the system works and educate or train people and predict phenomena and behavior. We develop scenarios to identify, analyze potential problems or threats. We can prescribe and remedy in time. Let me give you an example of a simulation. Suppose that you are in the Manhattan, New York City. You use a ride-hailing app to get a car. The assignment authority will dispatch the nearest car to you. The driver picks you up and then take you to your destination. After drop-off, the driver has to think where they will go. Depending on each driver's behavior, different phenomena will manifest. One obvious problem is what is the best strategy for both drivers and passengers in terms of search time and wait time. That was Geospatial Cup 2019 challenge. We use the taxi data. We have a pick up and drop up information. We build a spatial temporal model to predict resources. How do we know whether our strategy score or not? Here, yellow dots are empty car and red dots are waiting passengers. In the morning, there are a lot of demands in the Midtown area, while many agents are still moving to the center on the left, and there are a few empty cars on the right. The left one is random destination approach, which is a baseline, and the right one is our solution. After the rush hour, many cars become empty. It means oversupply. In this case, there's not much thing we can improve for it. With visualization, we can analyze how strategies work in the simulation. This is just one simulation, meaning one of the many possible worlds. To evaluate the efficiency of the strategies, we need more simulation runs in various environments. In this specific problem, the three measures were given: the search time, wait time, and resource expiration rate. From the result, we can observe that the more drivers in the world, the more competitive and the more uncertain. The reason why this huge uncertainty exists is because the amount of the resources are different depending on the day. Due to time constraint, I will not dive into the detail, and for more information about the method, please read our paper. What would be the most uncertain things at this moment? Maybe the matters directly or indirectly related to the COVID-19. The social distancing work, can we reopen the business? How many people will be infected? There are so many questions we are not sure. I'm going to touch these issues with the potential of geosimulation capabilities. Let me briefly introduce the abstract model and modeling and the simulation process. We have a problem entity or system that we want to model. Then we develop conceptual model in a suitable representation. Then we implement the computerized model, and we conduct experimentation, then comparing with the system. This process will repeat with the validation and verification. Then how can we model the epidemic in a geosimulation context? Here, our goal is to investigate the spread of general influenza-like diseases. We develop a geosocial model that simulates the patterns of life. Since I have another presentation about the patterns of life model in the next session, now I will not go into detail here. When it comes to behaviors, agents follow simple routines such as working, commuting, eating, and visiting facilities. In our simulated world, such facilities serve as a hub for spreading contact or proximity-based diseases. We adopted SEIR model, one of the well-known epidemic models. We ran simulation with 5,000 agents. After one period, we introduced the virus to the world. There are 4 states. Initially, all the agents are represented as a white circle, the meaning agents are susceptible. Once an agent is exposed to the virus, it turns into orange. After incubation time, the agent becomes infectious, which is represented as a red circle. The green agents are the recovered from the disease. The graph on your right shows evolution of the social network, and you can see how the disease spread in the social network as well as in the spatial network on your left. The chart in the middle shows the number of infectious agents over time. 2 graphs on the bottom show the average social network degree over time and distribution of the degree. When the number of infection reaches epidemic peak, you can observe that this is spreading influence social network. This is just one of many possible worlds. What will happen if there's no prescription in this world? This chart illustrates progression of the epidemic. Here the x-axis is time and the y-axis the number of cases with respect to the states. Each curve represents one possible world in the simulation, and the settings of all the runs are the same, and we just changed the random seed. From the sufficient number of the triers, we can obtain the mean and confidence bands like this. What you normally see in the COVID-19 dashboards is the blue curve. You may notice all agents are affected in the end. The simulation predicted the gloomy future. How can we make the future brighter? Now we will consider experimentation in the simulation process. Experimentation can be used to aid decision making. We often develop and simulate different scenarios to see the impact of events such as epidemic outbreak. Based on initial result, we may want to develop some policies and evaluate them. We will end up with optimization in huge search space. Each run is computationally expensive. So to design efficient experimentation requires significant effort. Then How can we streamline experimentation? One of our papers provide the solution, including workflow and a framework using runtime interventions. With the framework, we developed the two intervention scenarios to mitigate the spread of the epidemic, wearing personal protective equipment such as gloves and social distancing order. Here, social distancing denotes avoiding social gathering. The 50% of the population followed the order. So, do mitigation strategies work? The chart on your left shows the comparison of the number of infectious agents between baseline and two interventions. Though we can observe the different groups of the possible worlds. In some possible worlds, there are super spreaders who are more likely to infect others, forming transmission chains. The right figure shows the number of new cases. In this scenario, PPE has a marginal effect, although it lowers the chance of transmission. The reason is that the disease we chose is very contagious. Even with such a lower probability, about 30 minutes of the social activity is sufficient to infect others. So PPE could not prevent transmission that much, while social distancing flattened the curve significantly. In this module, I introduced the geospatial simulation as a paradigm to handle uncertain spatial temporal data. Among many approaches, I focused on the agent-based modeling, which is a bottom-up approach. The geospatial simulation is a white box model so that we can easily understand and interpret the models and result. It is a great tool in predictive and prescriptive analytics beyond understanding complex systems. These are references, and thank you for your attention. If you have any questions, we would be happy to answer them.